like dinosaurs in Star Wars.
Welcome back to Edpuzzle. That was Professor Levi telling you about dinosaurs in Star Wars. We left off talking about how different types of groups may be activating or deactivating. This actually leads to an interesting problem with Friedel-Crafts alkylations. We already know there are other problems with Friedel-Crafts alkylations. They rearrange. They also don't work if the ring is strongly deactivated. But there is an even more important problem. The products are always more active than the reagents, so they will continue to react. To get around this, we usually just acylate and then reduce. Some of our aromatic substituents are acid-base active and will have different properties in different environments. Look at the phenol on top. Is it more active in strong acid or less active? How about the N,N-dimethylanilene in the second row? Is it more active when it is completely protonated or less? Look at each of the four forms shown. What are the ortho-para directors? Which are meta-directors? We can see that a phenol can actually react in some circumstances even without a strong electrophile because the phenol is partially deprotonated in water and becomes so active that multiple additions occur without any catalyst. However, in acid, the activity plummets, which allows us to get a single addition product. Similarly, under mildly acidic conditions like acetic acid solvation for nitration, the small portion of the amine that remains deprotonated is far more active than the protonated form and reacts as an ortho-para director. On the other hand, with concentrated sulfuric acid, practically no amine is deprotonated and the ammonium can only function as a meta-director. Directing effects for electrophilic aromatic substitution are relatively straightforward for monosubstituted benzenes, but are often more complicated for disubstituted benzenes. The simplest case for directing of a disubstituted benzene is where both directing effects lead to the same location or locations. In the diagram shown, this is the case. The methyl directs to the ortho positions, while the nitro directs meta to the same locations. If the methyl and nitro groups are not aligned like this, we need to consider which positions are most active, or which intermediates will have stabilized resonance structures. Typically, stabilizing or activating features will dominate the directing in a ring. This makes sense when we think about the stability of the resonance structures formed. Remember that not only the number of resonance structures, but also the quality of resonance structures really matters. In the top intermediate for directing, dominated by the nitro, there are 3 resonance structures that all have the same energy. This doesn't offer any real advantage or disadvantage over the resonance structures for benzene. In the bottom intermediate, there is one resonance structure where the carbocation would be immediately next to the nitro. That's terrible, and it contributes almost nothing. On the other hand, there is a resonance...
Can I tell how the dinosaurs died?
Yeah, why don't you tell them how the dinosaurs died?
Volcanoes and a Chicxulub asteroid happened, and that's why the dinosaurs died out.
That's right, volcanoes and the Chicxulub asteroid. So on the other hand, there is a resonance structure with the methyl stabilizing the carbocation, which contributes a lot. It doesn't matter that we have one crappy resonance structure. The good one more than makes up for it, and the ortho-directing from the methyl is far preferred. Benzene is not the only aromatic ring that can go through substitution. It's just the simplest. Each of the molecules shown above, there are multiple distinct positions with the reactivity tuned by unique character of the ring. Naphthalene has 2 positions, both an alpha position and a beta position. Think of the other aromatic as the main functional group. The alpha then would be the next position over, or the benzyl if we had a single ring, and the beta position is 2 over. If a group adds at the alpha position, there are 2 resonance structures that are fully aromatic still. If a group adds at the beta position, on the other hand, there's only 1, so alpha substitution is drastically preferred. Similarly, with pyrrole, the 3 reasonable resonance contributors shown in the second set of resonance intermediates make the 2 substitution much more reactive than the 3 position, which is shown on the bottom. While electrophilic aromatic substitution is the norm, in particular situations, nucleophilic aromatic substitution is possible. The mechanism is different than anything we've seen before, because we can't have a simultaneous attack like an SN2 reaction, and we can't have the formation of a carbocation like an SN1 reaction. In nucleophilic aromatic substitution, the nucleophile attacks first, which is only possible if the resonance withdrawing group leaves a particularly positive carbocation. If a leaving group is placed at the ortho or para position to an electron withdrawing group, the initial addition is stabilized by the withdrawing group, which can then kick out the leaving group. Under really high pressure...
Can you tell them I have this?
Yeah, Levi has an owie that he'd like you to know about. Under really high pressure or temperature and strong bases, nucleophilic aromatic substitution can occur without an electron withdrawing group. The substitution needs to be different again. It goes through an alkyne.
When I was Grandma Betty, my great grandparents, when I was coming back from the mailbox to give him my grandparents letters, I got my owie.
Yeah, you fell a little bit. You okay though? They'll be glad to know that you're okay. This would be an elimination-addition reaction, but the initial elimination is not fully an alkyne. The second pi bond is very weak because the ring doesn't allow for the typical linear geometry. No catalyst is needed for the addition, as the benzene is incredibly reactive. Any strong base under sufficient conditions will be able to substitute like this. Potassium amide is more basic, and so it requires less increase in temperature to get the product. When we start thinking about synthesis for aromatics, the order in which we install substituents will determine the relative positioning. Think if we first install the chlorine, since the chlorine directs ortho and para, we will never get the desired metaproduct. We need, in this case, to nitrate first to get the appropriate directing. Try to identify which group would need to go on first in each case. Pay attention to not only the directing effects, but also the activating and deactivating effects in reactivity. Bonus points for the last one. Pause to give yourself some time. The first molecule has a methoxy, which is strongly activating and also ortho-para directing. It also has a bromo, which is para directing and deactivating. We don't have any direct way of installing a methoxy on a benzene. If we started with the bromine, we'd lose it when we add a group and convert it to methoxy. For that reason, we need to install the methoxy first and then the bromo. We can install a methoxy a number of ways, perhaps by installing a bromine and then going through nucleophilic aromatic substitution in sodium hydroxide at high temperature. This would give us a phenol, which we could react with methyl iodide to get anisole, which can then be brominated again to get a mixture of the ortho and para products. We get mostly para because of the size of the methoxy. An alternate route to phenol through a Sandmeyer reaction, a nitration, then a reduction of the amine, or two of the amine, oxidation of the diazonium salt, conversion to alcohol, etc., would also give the same product. The second product is much more straightforward. Either we could install the nitro first, which is meta-directing, or we can install the acyl first, because that's also meta-directing. And both are deactivating, so we'd have single substitutions. The third reaction can only give the correct directing if the ring is alkylated with the methyl first, followed by nitration. The final product is a little bit more complicated. Note that each group is an ortho-para director, but the groups are positioned meta to one another. Obviously, we can't react with these groups and get the geometry indicated, but we can react with not these groups. Let me explain. We've talked about reactions that will specifically modify particular groups on an aromatic in the last sections. Often we modify the group. When we modify the group, it changes their directing behavior. Being careful about the order in which we do this allows us a lot of control over the relative positioning. For example, we can install a nitro in order to install a metachloro, but the nitro can be converted to an amine, then a diazonium, then an alcohol through the Sandmeyer reaction. This is obviously not the only change we can make to the groups in the directing. One of those changes is that alkyl groups can be oxidized to switch to meta-directing, or acyl groups reduced to switch to ortho-para-directing. Amines can be ortho-para-directing, but can be meta-directing in concentrated strong acid, or they can be oxidized to become meta-directing nitros. Nitros can be reduced to amines and yield the ortho-para-directing too. And of course, the Sandmeyer reactions offer an enormous level of control, allowing either of the nitrogen groups to ultimately be switched to most other things. Amines yield a lot of control, but they also have an interesting problem with many Lewis acid catalysts like aluminum trichloride. The nitrogen will react better than a halogen and will form a really deactivating adduct. Protecting the amine as an amide is both fairly easy and fairly easy to reverse. We can also use protecting groups to help give ortho products only. For reference, para is usually easier to access because of sterics, so we can easily and reversibly install a sulfonyl group at the para position. With a sulfonyl at the para position, now only positions ortho to the original group are available. Since sulfonation is easily reversible, the group is removed on the completion of the reaction. A similar scheme involving an amine converted to an amide can protect against adding a halogen too many times, which can then be removed. The amine can be removed through a Sandmeyer reaction. This final slide is a text summary that couples well with the summary that we see in the tables at the end of the chapter. I'm not going to read this off to you, but I trust that you can review it at your own convenience.